Hey guys, back to the peak of the week. So you see what's going on the stock exchange, on markets. So crude oil is dropping down, so dollars is rising versus like at least rebels. So what it means that I decided to pick up something connected with functions analysis. And that's typical and core of derivatives application is to explore stationary points. Of course, this is peak of the week, so that's why it should be a bit challenging for you guys. So that's why I decided to make it a bit more complicated. So as you can see, functions with the parameters. So what it means, let's have a look at the problem. So you have the given function x cubed plus bx squared, and where a and b is just coefficients, you need to find in terms of a and b and classify the stationary points. So that's why right now what you have a cubic polynomial with some sort of general coefficients. It's right time to explore, okay? So pause the video, try to do by your own, and let's get started explaining. Okay, so the first track, what I'm gonna do is to explore general behavior of the cubic polynomial. So you understand that in general way, it can be, let's say, rising function, yes, depending on a coefficient, and falling. So depending on a, that might be polynomial sort of this way, when a is more than 0, or vice versa. For example, this way, if a is negative. So that's general behavior. However, to provide a bit more accurate analysis, however still brief, we can explore zeros of functions. So zeros of function. And this is the first step. So y from x equals to 0, that means 0 of the function. And we try to solve this cubic equation. We factorize it in advance, x squared, that you can factorize that, plus b, x plus b equals to 0. So that's why we will have actually 3 solutions. I hope you are not amazed about x1 and 2 coinciding. That's very significant. I'll explain to you why in a moment. And what about x3? The third solution is negative b over a. Okay, so the first solution is not depending on coefficient a and b, while the third one, it will depend on coefficient b and a. Okay, so right now what I'm going to say that for the third solution to exist, a is not going to be equal to 0. We'll explore the case when a is 0 later on, but right now we assume that if a is not 0, we can have the third solution right now. Okay, so what it means in terms of our behavior. So let's set up again y and x set. So this is y and x set. And what we're going to do right now is just to try to plot the general polynomial depending on sign. So indeed, if you have a is more than 0, the sign of course for x3 is going to be depending on b as well. But what about x1 and 2 equals to 0? That's actually 2 solutions, but there is still 1 point. What it means that in this case, the polynomial will touch the x-axis here, okay? It's not going to cross over, so it will touch. So that's why you'll have 2 solutions, and that's the key idea. Okay, so that's why in general we might have the following polynomial that might go something like this. In this case, definitely a is negative, and that's one point that delivers 0 to the function. Or it might be rising polynomial, and in this case we might have some like this, okay? In this case, a is more than 0. But this is not only all the cases that we can get and that, because b will also have some influence on the point, okay? And to play with coefficients, I'll offer you to plug some values. For example, we can take a equals 5, not 5, just positive and negative 5, and let's take b equals, again, positive and negative 3. And let's explore actually 4 cases that might have in this way of analyzing. So I just made preset for the graphs. This is function fx, and for fx, so both cases we took b equals to positive 3, while a here is negative, so a is negative for fx, so that's why it's fallen polynomial. And as we confirmed our investigation, so we have the touching position for x equals 0. So in this case, we have 1, 0 of the function. Another 2 zeros, which is actually negative b over a, that's x3, we have depending on the sign of b, so and a. So in this case, if a is negative, so this value is going to be, just let me zoom in a little bit. Okay, this value is going to be negative b over a, so that's why b3, and a is negative, so that's why it's 3 over 5. So generally, x3 is positive, so that's x3, okay? This is x3. That solution in general form, negative b over a. Okay, and in that case, obviously it's going to be negative. So in this case, x3 is negative 3 over 5, negative b over a. But you understand that for this case, a is positive because it's 5. So that's typical behavior. However, what if b is not 3? What if it's negative? We might have the second case. So b is negative 3 in this case, and we have 2 options, okay? When a, the leading coefficient, is negative, so that's why this is less than 0. And we have the first, again, the third solution, x3, which is, because b is negative in this case, we will have negative 3 over 5, right? Okay, b is negative, a is negative, negative 5, and we still have negative sign, okay? For that case, I didn't set up, oh yeah, I set up h function. So in this case, a is positive, it's 5, so we will have 3 over 5. Okay. Correspond to actually general behavior and general analysis for what we have. So we found those zeros, and now we actually already know that in both cases, when we will step into analyzing of using derivatives, when we'll be analyzing stationary points, okay, we already have a brief picture how it behaves, okay? So let's get and try to provide their derivative analysis for define stationary points. Okay, so what we have, the first, we are going to have the first derivative because dy dx and the stationary point should be equal to 0. So in other words, y prime or dy dx differentiate with respect to x will give us 0 at their stationary point. Okay, stationary point. So that's the necessary condition. Okay, that might be a point of local maximum, local minimum, or even a point of inflex or inflex point. Okay, so let's differentiate. So y prime is going to be equal. So a and b we consider as constants, like some numbers. So that's why we are doing 3ax squared plus 2bx. Okay, and we equate that to 0. If we factorize, we'll get x1 equals 0. That's the first stationary point. And if we're express x2, so that's going to be negative 2b over 3a. So we've got, in total, we've got 2 stationary points, x1 and x2. And right now, what we can do, we can plug those points into y. So y from 0, and this is y1, and y2 from negative 2b over 3a. Okay, so right now we're just plugging those points, and we try to establish the value for y because we need to find points. Okay, so that's why y from 0 is obviously 0, and from negative 2b over 3a, if we simplify that, we'll get 4b cubed over 27a squared. Okay, and as you can see, y2 value depending on b and a at both. If a is not equal to 0, so the sign for y will be defined by b, but the value both depending on both numbers a and b. Okay, so finally we've got two stationary points. Let's say S1 stationary points, which has coordinates 0 and 0, and S2 negative 2b over 3a and 4b cubed over 27a squared. Okay, a squared. Okay, I hope it's clear. So a squared. So just this one. Okay, now what we're going to do, we want to make sure that we can differ which is maximum, which is minimum. So we differentiate twice. So y2, y prime the second time. That means we differentiate this expression one more time. Okay, and what we're going to do, we just trying to make differentiation. So 6ax plus 2b. Okay, so, and of course the value will be depending on both a and b, and also the value for x. So that's why first what we're gonna do, we plug the first point and say, okay, y the second derivative from the point 0 is gonna be 2b. Okay, so 2b, and depending on b sign, there might be positive. This might be positive and negative. And we know that if, so we can state now, if b, in this case, if b is more than 0, so we have point 0, 0 to be the minimum. If you're not sure, just remember parabola or basic parabola x squared. So if you differentiate twice, you'll get 2. And 2 is positive, so that's why it's minimum, okay? So that's the first case. So what about the second point then? If b is positive, we'll get the following. So y, the second point should be the point of maximum, right? So if b is positive, so the second point, let's take second derivative and plug the second coordinate negative 2b over 3a, and we'll get, if we plug that, I bet that you'll get negative 2b. So negative 2b, and in this case, obviously if b is positive, so the second point with coordinates x, so that was s1, so this is s2 with coordinates negative 2b over 3a and 4b cubed over 27a squared. So that's the point of maximum. Okay, so let's go back and check it just quickly. So if b is smaller than 0, so this is the condition. So we might have the following. So if b is positive, we definitely have this case. We definitely have this case. So b is positive, it's 3. Depending on sign for a, we have different types of polynomials. However, still we know that x equals 0 is the point for local minimums, and we can check it. So x equals 0, that's minimum. What about maximum? Let's go back and see, okay? So we have maximum here and we have maximum here. Of course, depending on sign, there might be positive and negative for x-axis, but they're both local maximum for two curves fx and gx. So that's why our analysis, brief analysis, will correspond to the general way of exploration. Okay, so the second case, let's consider the last case when b when b is negative. So if b is negative, point S1 with 0, 0, just let's have a look at the value. So we plug the first point S1. That will be definitely maximum, okay? So we'll have max point. And what about S2 with value negative 2b over 3a and 4b cubed over 27a squared? So that's definitely is going to be the point of minimum, yeah? So because we have negative 2b, so that's why we have positive, so second derivative is positive. Okay, so let's just go back. B is negative now, and we have exactly this case, so b is negative 3. And in both cases, let me see, so for example, for px when a is negative, so we still have max, okay? And for the sort of orange curve, hx, so a is positive, but still have local maximum again. So that would correspond to our general analysis, okay? And another point should have minimum. Let's have a look. So another point, which is here and here, depending on sign for a, of course, they both are local minimums. So that's also correspond to the case. But remember, we didn't explore the case when a is equal to 0. So let's correspond to that case, what will happen? So generally, we'll have that y from x is simply bx squared. And now this is parabola, okay? For that case, when a is 0, we just simply know that sign will be dependent on b, but if b equals 0, so we have y equals 0, and the gradient, so it's just a straight line, horizontal straight line. So gradient is 0 definitely, but there is no any maximum or minimum point because it goes at the same level. But if b, so if b not equals to 0, again we have two cases for parabola. So we have upside down parabola and goes up. So in both cases, we can find that it's going to be a maximum for b negative and minimum for b positive, okay? So as you can see that we have specific case, but what if b equals to 0 and a is not equals to 0? So that's how we can explore. We have a basic cubic function with a scale factor of a. And you remember that if b equals to 0, so actually present this on the graph, definitely we have two types of curves. So the first curve is gonna go like this if a is positive, and another type of the curve is gonna go vice versa. Goes down. So in this case, a is negative. But however, still dy dx is going to be 0. Why? Because if we differentiate, so we'll get the answer in terms of b, as you remember. So we found that y prime, yes, we have 2 points x1 and x2, and both that will be the same because b is 0. So that's why this point x equals 0, x1, 2, and 3 equals to 0. That's going to be the point of inflex point. So inflex, that means no local minimum, no local maximum. So that's the point where you have different concavity. But if you explore in terms of the gradient, so you see that gradient is positive here, so as well as here. So on both sides of that point of the inflex, gradients still the same. While if you have stationary points like local maximum, local minimums, or in other words, turn points, so the gradients should have a change, right? Okay, so I hope that you're not gonna be afraid next time if you can see some like polynomial in general way or another function with parameters. There's no problem, just play with numbers like we played, and make sure you have just solid instrument of investigation. Investigation is still the same, so there is not something new, but I show you how to provide analysis in general. Hope you like that. If you're new here, please subscribe. I'll appreciate every single subscriber. So my subscribers, I want to shout out big thanks to you guys. Thanks for your support. Thanks for watching. I hope I'm making nice videos for you, at least very helpful and informative. So please see you next time. And by the way, don't forget to visit A-level Zillion's classes for more exploration in A-level stuff. Peace.